That's impressive. It always goes wrong. Okay, so I don't have to introduce myself. I came here from Berkeley, but I also spent part of my time working at Asia A in Taiwan. They pay half my salary, so I wanted to mention that we all like them. I'm talking about stuff based on the Overwhelmingly Large Simulations project, or OWLS for short. In this project we have several simulations, all simulating a representative part of the universe, talking mostly about the boxes that are either 25 megaparsec on a side, or 100 megaparsec on a side, depending on the redshift, because the small box only goes down to redshift 0, but it has higher resolution, so therefore it's still very useful to use. At redshift 0 we only have the lower resolution, larger box. We use smooth particle hydrodynamics, which means that the mass is discretized as particles, and we have dark matter as well as gas, and then gas follows a star formation prescription and can turn into stars. The idea behind these simulations is that they're all very similar, but except for one aspect in the simulation. So in some simulations we do not have metal line cooling, in some simulations we've added AGN feedback, and then the idea is that we can so none of these simulations reproduce the universe in exact detail, but we can see what the difference is between simulations by varying only one aspect of the simulation. So I'll be focusing on what the effects of supernova feedback and AGN feedback are. So this is just an example of a 10 to the 12 solar mass halo at redshift 2. This is for our higher resolution simulation. You can see the same halo 3 times. So on the top row you can see the density, and the bottom row shows the temperature. On the left it has no feedback, so there's just all the other thermal processes involved in galaxy formation. So this galaxy will have a much larger stellar mass because there's nothing preventing star formation. In the middle there's what the halo looks like. I guess maybe I have a circle to show you what the virial radius is of this galaxy. This one has supernova feedback only, so you can see that the high temperature region is slightly larger, and then on the right you can see a model that has both the same supernova feedback as well as AGN feedback, and then the temperature, the high temperature region becomes even more extended, but also reaches a much higher temperature. But what I'd also like to point out is that you can see these filaments that are penetrating the halo and going to a radius much closer to the galaxy. They look very much more disturbed as you add more and more feedback, but they're not completely destroyed. So they're disturbed, but they don't vanish. They're still there. That's just an aside. That's the virial radius. So I will be mostly looking at the difference between the simulation with and without AGN feedback. And this is, if you use a very simple, what is this, the specific star formation rate criteria to just say how many of these galaxies are quenched and how many aren't. So I'm only looking at the 514 most massive galaxies at each of at all these redshifts. You can see that without AGN, that's the dashed red curve all the way at 0. There's absolutely no galaxy that would qualify as a quenched galaxy. They're all massively star forming, even the most massive ones. But if you add AGN feedback, then this quenched fraction increases from 0 at redshift 5 to 90% at redshift 0. So that's just to set the stage of what these simulations look like, because I'm here really to talk about accretion rates. So I'm plotting the specific gas accretion rates onto as a function of halo mass. So this just means that I took the accretion rate and divided by halo mass to scale out the linear dependence. This is a simulation without any type of feedback, and you can see that it's almost linear. There's a break also at about 10 to the 12 solar masses. That's because above the break I've used a low resolution, large volume simulation, and at the lower masses I've used the smaller simulation, so it doesn't have these high mass objects, but it has better resolution. So without feedback, gas accretion onto halo, so this is the gas accretion measured at the Vero radius, does approximately the same thing as a dark matter accretion rate does, that also scales linearly with halo mass. But if you start adding some extra feedback models, so now I've added supernova feedback. This still doesn't include metal line cooling, by the way, but the difference between the two simulations is this adding supernova feedback. You can see that for high mass halos nothing changes, but for low mass halos you start getting a suppression of the accretion rate. So this is not the net, it's not inflow minus outflow. I've not subtracted the outflow, so it's just the gas that manages to get into the halo at redshift 2. For these low mass halos, it's actually suppressed by a factor of 2 or 3. No suppression at high redshift, at high halo mass. If you add metal ion cooling, nothing changes. It is exactly the same, and that's because cooling of the gas is not important for accreting onto the halo. So this will be different for when we look at galaxies later on. AGN feedback, I've already said, is what I'm going to be talking about most. We again get a suppression, but now mostly at high masses. So again, the accretion rate onto halos is lower by a factor of 2. So it's not a big reduction, but it'll be different for galaxies. So this is the difference between halo accretion and galaxy accretion without any type of feedback. So you can see the galaxy accretion rate is always lower than the accretion rate onto halos, and this the difference is largest at the highest masses because the temperature of the gas is higher in higher halo masses because it shocks to the virial temperature, then cooling time is longer, so it'll take as opposed to halos, now cooling becomes very important because the gas can only accrete onto the galaxy after it has cooled, and because this takes longer in higher mass halos with higher temperatures, you get a large reduction of the accretion of the galaxy accretion rate compared to the halo accretion rate.
So operationally, what is the definition of galaxy accretion rate? Is it the amount of gas that flows radially throughout some radial bin, or that drops below a temperature of 10 to the 4? Or?
So what I've done here, but you could do anything, is define the galaxy as the star-forming gas in our simulation. So that's a density cut, because it's only star-forming above 0.1 particles per cubic centimeter. So it's all the gas that is added in the center that reaches a density above 0.1 particles per cubic centimeter. So the gas that's added to the star-forming part in the star-forming gas in the simulation.
But how do you subtract the effect of the feedback?
Sorry?
How do you subtract the effect of the feedback then?
How? I'm not sure I understand.
Well, the gas, it becomes star-forming by cooling, and then also it becomes non-star-forming through the feedback.
That's true.
So how do you separate those?
I mean, you compare a simulation with and without feedback, and then you can see what the difference is, and that's how you determine what the difference is between, that's how you determine the effect of feedback. So, I can do that now. So this is the title is wrong, this is the galaxy accretion rate. And then if I, so you can see that actually the mass at which galaxies are most efficient at forming stars is at very low masses, at 10 to the 10 solar masses. But if I add feedback, it looks very different. So this is only supernova feedback. So it reduces the gas accretion rate onto galaxies at low halo masses by a factor of 10. and at high halo masses it actually increases a little bit because less gas is locked up in low mass objects and is available to accrete at a lower redshift onto more massive galaxies. So you have a small increase at higher masses, actually getting less quiescent massive galaxies. So you maybe want to have feedback also be effective at high halo masses. So this is what happens when you add metal ion cooling. You get an increase by about a factor of 3, especially around 10 to the 12 solar masses, where this galaxy fueling is most efficient, just because you have more cooling of the gas, because metal ions are now also contributing. And then if I add AGN feedback, it again can reduce the galaxy accretion rate by an order of magnitude. You can see that the difference between the two simulations, but at high and low resolution, is very large, just because this model is not completely converged. But I'm also not saying that this is like the value for the gas accretion rate, but it's at least, it shows you what the difference can be if you add AGN feedback to a simulation. You can get an effect that is an order of magnitude. So it's at least important to consider when you do these types of simulations.
The increase at high masses is due to the fact that the gas is ejected by a feedback into a cold phase.
So the increase adding supernova feedback, you mean?
Yeah, I guess I'm wondering if you ejected that at 10 to the 7, then it would be the same as the plasma, and it should be aligned with the black curve. But you're getting this increase presumably because when you eject the gas from the satellites, it's in a cool phase that can then cool onto the central galaxy.
But I mean, do you mean by adding AGN feedback, you actually decrease
No,
the
I just
galaxy
mean the
accretion?
difference between the black curve and the red curve.
Yes, so that's partly because there's less gas locked up in no mass objects, and partly because there's more cooling. So some of the gas that doesn't manage to cool in a primordial metallicity simulation does manage to cool and reach the galaxy in a like more realistic model. And actually our AGN model, so at these high masses, our AGN model just manages to reduce the galaxy accretion rate to the no feedback primordial value, but at least it's much reduced from the supernova plus cooling model, which is all included in the AGN model also. So let's see. So we can look at what the galaxy growth is at fixed number density. So I've already shown you the quench fraction, and this is what the total mass, the stellar mass, and the gas mass look like as they evolve from redshift 5 to redshift 0. It looks approximately, within a factor of 2 or 3, it looks the same if I actually traced progenitors or descendants. Mostly descendants look the same, but progenitors have only a difference of a factor of 3 or so. So it doesn't really matter what I show. But I would like to show the difference if I don't use AGN feedback. So you can see that there's approximately no difference in the total mass, so dark matter is not very much affected. The stellar mass without AGN feedback is much higher, so before it was the stellar mass was different from the total mass by 2 orders of magnitude, and now it's just over 1 order of magnitude, and the gas mass is even more reduced because of AGN feedback. And actually, so from redshift 3 to redshift 0, it decreases by more than an order of magnitude, but only with AGN feedback, because it stays approximately constant if I just have the model with only supernova feedback.
Just a quick question, is the difference in the total mass because gas is ejected from the halo? Or because the structure is changing? And so the virial radius is different?
I'm not sure. Could be either, but I imagine that it would be that there would actually be less mass in a fixed radius. I mean, this is not a fixed radius, but if it were a fixed radius, I would imagine there's slightly, order maybe 10% less gas inside. But
Marco Velashik looked at that in a paper, and he isolated the two effects. It's mostly the ejection.
Okay.
So if I now look at how this galaxy grows, so I'm showing you the stellar mass growth as I did before, which is a solid curve. But then if I look at how the mass builds up only inside the central proper 5 kiloparsec, you can see that after a redshift of 2-ish, there's not much mass added to the center anymore. And then again, so there's a big difference at low redshift, and that's only present in a simulation with AGN feedback, because if I don't do that, there's no quenching. So the central part of the galaxy keeps forming stars. The stellar mass is much higher, but it's also all added to the central 5 kiloparsec, because there's almost no difference between doing the full galaxy versus doing only the central part, which is inconsistent with observations, as I'm sure some of you know better than I do. So back to accretion and star formation rates. So this is, I'm showing you in light blue is star formation, and in purple is gas accretion, but now I have taken into account outflow, so I'm now doing inflows minus outflows, so it's a fixed, it's actually what flows through a radius of 15% of the virial radius. So that what's actually how the galaxy is actually growing due to gas accretion. So the dotted part of this gas accretion curve is actually where there's more outflow than there is inflow. But what I've added also is how much stars accrete through this same radius. So call that star accretion, but of course you can call it merging, because this is the only way you can add stars to a galaxy. So I'm including everything, right? So this is major, minor, and miniature mergers. But you can see that there's kind of 3 regimes, because at very high redshift, redshift 5, the gas accretion dominates. It's higher than the star formation rate, so you actually increase your gas reservoir. The star accretion is not important at all. But then at intermediate redshift, between 1 and 2, star formation is the highest, so you start depleting your gas reservoir. And as the star formation rate drops, the accretion rate of these galaxies, the star accretion rate, so the merger rate of these galaxies actually starts dominating. So most of the stars that are added at low redshift are actually added through merging. And this, again, very different if you don't include AGN feedback, because so the star accretion stays approximately the same. The gas accretion rate is much higher, and so is obviously the star formation rate, because that's completely driven by the gas reservoir. So this is so if you had no AGN feedback, star formation would still dominate at redshift 0 by an order of magnitude. So I'd like to finish with my conclusions. Efficient feedback reduces the gas accretion rate onto halos by a factor of 2 or 3, but it has a much larger effect, up to an order of magnitude, if we look at a gas accretion onto galaxies. Metal line cooling is also important, because it increases the gas accretion rate by up to a factor of 3. The most efficient galaxies live in halos of about 10 to the 12 solar masses. Without AGN feedback, the galaxy growth all happens in the center of these galaxies. But with AGN feedback, they grow through. So at low redshift, they grow mostly through mergers, and this mass is all added in the outer parts. Thank you.
Plenty of time for questions. Christoph?
So did you correct for this artificial star formation in this dense clump that is stripped off the galaxies?
So you mean by satellites and
Exactly.
stuff like that? So I've corrected for that by only looking at the central object. So I've looked only at the star forming gas inside 15% of the virial radius. So most of the artificial clumps star forming clumps are excluded, as are all the satellites.
But dynamic friction also, or numerical dynamic friction, drags them down. So that would sort of count as your accreted star formation, right?
So
you would accrete those
yes,
stars
so you would
that are
still
formed because of dynamic friction.
yes, you would still
So
accrete
if
those.
in your sort of account is those would be accreted stars.
Yes, if they have formed stars before, yes, then they would count as accreted stars. Correct.
It's negligible effect on the scalable plots.
Depends on how big are your halos that you're looking at.
These are the mass.
These are the 500 most massive, so they're 10 to the 13 solar masses on average.
As you said,
Average.
it's not such big effect, so it's bigger in smaller clusters.
Front?
You keep using the word agent feedback as something that's set in stone.
Right,
Could
our
you just-
model.
Yeah,
Yes.
could you just say a few words
course.
about how you implemented
Of
the
course.
simulations?
This is, I should have done that, but this is a model where, so the black hole accretes according to a Bondi Hall-Littleton prescription, so you know how much gas is accreted, you store the energy until you have at least enough to, you have enough energy to heat at least one neighboring gas particle to at least 10 to the 8 Kelvin. So this assures that you're doing effective feedback, because if you do it every time step, you heat it to 10 to the 6 or 7 Kelvin, and it does nothing because it's cooled out immediately because the density is so high. So it's very important to have a high minimum heating temperature, but it's all thermal feedback.
But that's then given to the one nearest particle, that's all the energy, all the thermal energy?
Yes.
And the radiative efficiency is assumed to be 0.1 throughout, or
I think it's
something?
0.15.
But
It's fit to the local black hole mass density, the observed black hole mass density, and doesn't actually matter much because it's self-regulated. So if you increase the efficiency, you just get smaller black holes with the same feedback, and the other way around.
On that point, so you assume you don't resolve close to the black hole, presumably.
Right.
So at some point you're saying, I just think this stuff will accrete.
Yes.
Is that right?
So there's a.
Everybody does?
Right. So there's.
Exactly. Yeah.
So the model, if you resolve this, the accretion radius,
It'll make a disk somewhere.
then you keep it at the rate that you can actually resolve. But if you cannot resolve it, which is often, then it's actually multiplied by a factor that scales as a density to the power 2, I think.
Okay.
But it's actually, so it's the accretion rate, because we're not resolving the right density, is actually boosted by this factor.
But in principle, it could make a disk and it wouldn't accrete at all.
Right, yeah,
Okay.
Yeah. true.
Could you just go back to the previous graph? And I was a bit surprised that the amount of gas and the amount of star formation don't track each other more closely. Is that just a misunderstanding of what you mean here by gas?
So the gas accretion versus star formation?
Yeah.
I mean, there's a delay, right? Because it takes about like the.
So what gas phases are you considering here? I guess that's.
So this is the. So this is any phase of gas accretion and goes into this radius of 15% of the virial radius. But at this radius, a lot of it will actually become star forming. But because it still has to cool to reach this.
Can this then explain why you have a peak where your gas accretion is higher than your star formation at low redshifts? Is this because it's all hot gas that's being accreted?
Possibly, but there's also a delay between star formation and gas accretion, right? Because like it first has to actually make it to the galaxy, and then there's still like a giga-year of star forming time. So I don't really dare predict what will happen in the future, but you can see it from the fact that the gas accretion already starts decreasing while the star formation still stays constant, and the star formation rate starts decreasing at a lower redshift. So there is this delay. So I'm not really. I would be surprised if there was a lot of hot gas at this at like 15% of the virial radius.
Okay, I think we had great questions. Let's thank the speaker again.